Hello TNA, and welcome to Lesson 8 of your GCSE level energy topic. Now before we get started on this lesson, I want you to make sure that you are ready to learn in this lesson. So that means that you have all the equipment you need, your booklet or the paper you're writing on, a pen, your feedback color pen, as well as a calculator for this lesson. If you're using your phone as your calculator, put it on Do Not Disturb mode so it's not distracting you. Or if you do have another calculator, just put your phone right away, again, so it's not distracting you, so you can focus on the lesson. So this is lesson 8, energy transfers in a system. So we've talked about different forms of energy. So now we're going to talk about how energy changes from one to another within what we call a system. So as always, before we get started on the lesson, we need you to turn your brains on with this knowledge check. So pause the video, do the knowledge check, making sure you have something written down for every single question. So here we have the answers to this knowledge check, correcting any mistakes you've made with your feedback color pen to make sure that you do have all the right answers written down. So as always, for these two especially, make sure you know what all of these letters mean. So you know that kinetic energy is equal to 1/2 times mass times velocity squared, or gravitational potential energy is equal to mass times g times height. So moving on, we're going to look at the conservation of energy. Hopefully from last lesson, you'll remember what the law of conservation of energy is. Writing it down now. Well done if you've written down that the law of conservation of energy is that energy can not be created or destroyed, only transferred. So, with that in mind, thinking about the fact that we can't lose any energy, we can't gain any energy, what happens to the energy stores and the energy transfers as we throw a stone in the air? So grab something, not a stone, but something that you can gently toss in the air. So stone in the hand at the point of the release. What energy store does it have right there? What is the energy store as it moves upwards? What energy store does it have at the highest point? Remember, it's not moving once at that millisecond it's at its highest point. What is the energy store as it's falling downwards? And what is the energy store in your hand at the point of catching it? So 1/2 second before you catch it. This one is also 1/2 second after you release it. What is its energy store? So I want you to write down all of those. All right, so hopefully at this point you have written down that at the stone in your hand at the point of release, it starts as chemical energy. Just before you release it, which changes to kinetic energy. As you let it go, you've given it that kinetic energy, the chemical energy, remember, stored in your muscles. So as it's moving upwards, it's losing kinetic energy and gaining gravitational potential energy. So as it's moving upwards, it's going higher in the air, so it's gaining gravitational potential energy, but it's losing kinetic energy. When it's at its highest point, that millisecond, it has 0 kinetic energy. It has no kinetic energy. It has all gravitational potential energy. So once it's at that highest point, all of its energy has moved into gravitational potential energy. As it's falling downward, it loses its gravitational potential energy, but it gains its kinetic energy. So at the point of catching, it now has lost all of that gravitational potential energy it's gained. So it is all in the kinetic energy store just before it hits your hand. So hopefully that makes sense to you. If you're struggling with it, physically toss something in the air and watch as it pauses and as it gains speed again as it moves down, and things like that. So play with something in your hand, tossing it gently so that you can see these energy transfers. So that initial energy store makes the stone move upwards is provided by the chemical energy store in the muscles. Then that goes into the kinetic energy and goes into gravitational potential energy and back again. So if we only compare the changes of the energy stores from the point it has been released, so that's 2 milliseconds after letting go, to the point where the stone's captured in the hand, so 2 milliseconds before you grab it again, the energy is the same at both points, if it is at the same height. So with this, we are making an assumption. So we're making an assumption that no energy exchanges with the surroundings, that the stone doesn't give any energy to the surroundings and it doesn't take any energy from the surroundings. So when you let it go, it has 100 joules of energy, and because none of that energy has left the stone, it's only changed from kinetic to gravitational potential back to kinetic, it will have again that same 100 joules once you capture it again. This is what we call a closed system. A closed system is one that doesn't exchange any energy with its surroundings. So it doesn't lose any to its surrounding, it doesn't gain any from the surroundings. So the energy can be transferred from one store to another, but the total amount of energy in a closed system stays the same. So if you're not working with the booklet, I want you to write those 2 sentences down so that you have them written down. A closed system is one that doesn't exchange any energy with the surroundings. So that means nothing, no energy going in, no energy coming out. So we know that because there's nothing coming in or out, and we can't create any extra inside, or take any out, or destroy any that's in there, we know that that total energy needs to stay the same. However, real life is never a closed system. So there's always ways for energy to escape. So useful energy, so this is called the dissipation of energy. So this is when energy escapes or is not useful. So in science, we describe useful energy as the energy transfer that a device is designed to produce. So an electric kettle, you turn your kettle on and we have energy transferred to the kettle by the electrical pathway. So why do you turn on a kettle? What is the point of turning on a kettle? Most of you will agree the point of turning on a kettle is to heat the water inside of it. So by using that electricity, we increase the thermal store of the water. However, unless you have a perfectly insulated kettle, you'll notice that the air around the kettle also increases. That's usually not why we turn on the kettle. We don't turn on a kettle to increase the temperature of the air around it. So that will be waste energy. So that's not the useful energy. You'll also notice that the kettle will make some sounds. So it's also producing some sound energy. Again, that energy isn't useful. That energy is something that is created but isn't useful. So this increase is not useful, as we want the energy to heat the water, not the air. So it can be described as wasted energy. Wasted energy transfers are unwanted energy transfers. I want you to think about another example where there's wasted energy. It could be any example in your life, but somewhere where the energy isn't all used in the way that you want it to be used. I'm going to use the example at the minute of a television. So a television, what is the useful energy of a TV? So the useful energy We have our light energy that's coming off so we can see the picture. And we have sound energy because we want to hear what's on the TV. The TV will also create wasted energy as light. Sorry, not as light, as heat or thermal energy. What other waste energy can come from the TV? So sometimes it makes unwanted sounds. Sometimes it has extra lights that we don't need, things like that, right? So we have the useful energy of the TV and the wasted energy is the energy we don't want. With that in mind, go to this checkpoint and what is waste energy? Write it down in your own words. Hopefully you have something along the lines of wasted energy is energy that doesn't fulfill the intended purpose, or energy that doesn't do what you want it to do, energy that is not what we want to use the energy for. So, thinking back to our initial example, where is of this throwing stone in the air, where is the wasted energy? What happens that creates wasted energy energy we don't use? So first write in your useful energies and then write down your wasted energies. So here are your green pen answers. Make sure you do have them down in your book. So as the stone is moving upwards, the energy we're using for the stone to go up into the air is the kinetic energy that we've put into the stone. At its highest point, it will have all gravitational potential energy, and so that is the useful energy that is there. The stone falling downwards is the gravitational potential energy that is pulling it down. And the stone caught in the hand, once it's in the hand, it's all, or the millisecond before it hits your hand, it's all kinetic energy. So what are the wasted forms of energy for this stone? So we have a mostly thermal energy. Because remember, most wasted energy in the universe is as thermal energy. So that thermal energy, it heats up because of the air resistance or because of the friction. So the same way when you rub your hands together, it heats up. When you wave your arm around enough, it's rubbing on the air particles and it is creating that thermal energy. This is why a meteorite, when it falls from the sky, it burns up, or when a rocket ship returns back to Earth, it gets really hot because of that air resistance. So at the highest point, because it's not actually moving, it's not creating any air resistance, and so there isn't actually any wasted energy coming off of the stone once it's at that highest point, because as I said before, it's not moving there. But as it falls down again, we have some kinetic energy that's being created, or not being created, being transformed from the gravitational potential store. And again, we have that thermal energy that it's being wasted as, and then once we catch a stone in the hand, it will make a sound once it hits your hand. So we have our thermal energy as well as our sound energy that is being created there. So with this, we look significantly more at various types of wasted energy. So when not all the chemical energy that we have in our muscles when we throw the stone is converted into kinetic energy, sorry. So we know that when you do any kind of moving, you get warm. When you go to PE class, you come back, you're warm, you're sweaty. That is because most wasted energy is thermal, or most of the energy created is thermal. So as I said before, when stone moves through the air, there's friction. So the air's thermal energy store is also slightly increased. So when the stone hits your hand, it creates a sound, and that increases the thermal energy store of the as well. So we want most unwanted energy transfers are into the thermal store. So we want to try to reduce this because wasted energy is, remember, what's our definition? Unwanted energy transfers is what we can't use. So our unwanted energy transfers, our wasted energy is energy we can't use. So we can reduce this wasted energy. We either need to reduce friction so that things slide easier, or by increasing thermal insulation. So just insulating things. So there are two ways that we can reduce friction. We can either use lubrication or streamlining. So in this case, lubrication means that it's made more slippery. So there's lubrication that we use in engines and things like that. So, and a lot of those are oils or oily things. So if you ever have been cooking and you've gotten some oil on your fingers, you know it's really slippery and that your fingers slide a lot easier. All right. Some things make it less slippery. So something like sandpaper, you don't want to add too much grit or something in there because that would increase friction. Streamlining has to do with the shape. Whereas you know that a race car looks very different in shape from a Range Rover. A race car is more streamlined so that there's less air resistance, so that the particles can flow past it easier. So you can think a race car is streamlined, a Range Rover is far less streamlined. So, or we can increase the thermal insulation. We know intuitively that certain things have less heat that come out of them than others. For example, if you pour hot liquid into a paper cup versus a styrofoam cup, which one will feel hotter to pick up? Yes, the paper cup feels hotter to pick up than the styrofoam cup because the styrofoam is more insulating. Activity 2 is a practical that we would do if we were in class, but unfortunately we can't at the minute. We do, however, have a video of it. So you'll notice this conductivity ring. It has 4 different metals along the outside of it. So the 4 metals that are part of the conductivity ring, please make sure that you copy this table here down into your books. So we have aluminum, there's iron, brass, and copper are the 4 metals that are each of these 4 pins. So as I said, there's aluminum, iron, brass, and copper. So the way we would do it in class is we would use Vaseline and some drawing pins, and then we would wait to see how long it would take the Vaseline to melt. The video you're going to watch uses instead some little bits of birthday candle and sees how long it takes for them to start melting. So we set up the conductivity ring, put the Bunsen burner underneath, and then we see which one starts to melt first, because that one will be the one that conducts the heat the most easily. So we do already know that metals conduct heat more easily than what? Than non-metals, yes. So metals conduct heat better than non-metals. This is something we know and that we've talked about from atomic structure. But these are 4 different metals. So different metals conduct heat a little more or less well, depending on the metal itself. So as I said, you have this table here with aluminum, iron, brass, and copper. So time for, we're not going to say pin to drop. We're going to say time for candle to melt. So you're going to watch the video, write in the times, and then answer the question, which metal is the best conductor? So which metal conducts heat the best?
We're going to look at the order in which these pieces of wax melt. It'll give us an indication of the conductivity of the metals. The 4 metals are copper, aluminium, brass, and iron. I've started the stopwatch to get a measure of how quickly it happens. Copper's the first to go. You can see the candle is melting. It's about 30 seconds. Aluminium's starting to melt. It's about 40 seconds or so. Brass is starting to melt. It's about 80 seconds. And there goes iron at 2 minutes 28. That's the final one. So the order seems to be copper, aluminium, brass and iron.
All right, and this last activity here is one that you can do at home. So you will need 2 beakers, or, because you won't have beakers at home, you can just use some cups, mugs, glasses, anything that can handle being filled with boiling water. Some layers of insulation. For this, you could use a tea towel, a scarf, a hand towel, any kind of layer of fabric that's about that size. A couple dish rags could work as well, even some paper towels. Some rubber bands. These will be used to hold the fabric to the cup. So if you don't have these, that isn't a huge deal. Just make sure that you wrap it carefully, wrap it tightly so that it doesn't fall off. 2 thermometers. If you have these, great. Even one that you can move between the 2, also wonderful. If you don't have them, you can do it without. And a stopwatch. You could use a stopwatch on a phone or on your computer or anything else to do that. So you want to wrap your insulating material, so whether that's your tea towel, your scarf, your dishcloths, whatever, around beaker 1, around one of your cups. Then you want to wrap several layers. You could even do, you have 1 cup with many 1 cup with a little bit, and 1 cup with none. You could do 3 different wines depending on how you want to do it, but it doesn't matter how many you do it. So you want to leave 1 around beaker 1, and then you want none around beaker 2. So beaker 1 will have insulating material, beaker 2 or cup 2 will have no insulating material. So place a thermometer in each beaker if you're able to. If you have it, you can place it in each cup and prepare your stopwatch. So you, very carefully, with mom and dad's help if you need to, will pour approximately 100 milliliters of hot water, of boiling water, from the kettle into each beaker. So just fill up each cup. All right, and then you'll start the stopwatch. So if you have a thermometer, take the temperature right at the beginning for each cup. If you don't have a thermometer, I want you to wait 1 minute or 60 seconds. And then carefully, without burning yourself, put 1 finger into each cup and feel how warm it is. All right. And then again at 2 minutes and again at 3 minutes. All right. So even though this table doesn't go on 2, so at 1 minute, 2 minutes, and 3 minutes. Again, if you have a thermometer, you can take your start as well. If you do not have your thermometer, do not put your finger into boiling water. Okay? So, and then you should be able to feel with just your finger how the temperature of the water changes as you go through this time. So, once you finish that, answer this question here. Does the thickness of the insulating material affect the rate of cooling? Even if you haven't done the practical, you can still answer this question because you will know the answer to it intuitively. Once you've done that, there's a knowledge and application check here that you can give a try to. Give it a go, pause the video, give it a go, and come back for the answers. So here are the correct answers for this knowledge and application check. For question 4 and 5, they can go either way. So you could have lubrication first and insulation second. That's absolutely all right. A higher thermal conductivity is which is more conductive. So which conducts heat more easily. So the higher thermal conductivity, we know wood is a nonmetal, and we know metals conduct heat more easily than nonmetals. So one factor which affects heat loss through a wall, the amount of insulation in the wall, or you could have said what the wall is made of. So both those things are essentially the same thing as to how well that wall will insulate. A second factor is how hot it is inside. So if it is very hot inside and very cold outside, more heat will travel through the wall. But if it's about the same temperature inside as outside, you'll have less transfer of heat through the wall, or less heat loss through the wall. If you've ever felt a stick out in the sun versus a stone or a brick, you'll feel that the stone or brick is much hotter than the wood. So it holds less thermal energy, it holds less heat. State of matter that has a fixed shape is a solid. State of matter that can flow, a liquid or a gas. You could also have used the word fluid because that talks about both liquids and gases. Again, if there are any questions about any of this, make sure that you do let your teacher know. Make sure you complete any follow-up tasks your teacher might have set, whether that be a quiz of some kind or anything else. And otherwise, until next time,